All right. So 6.1, confidence intervals for the mean. For large samples, this is for sigma known. So this is 6.1, section 6.1 in your notes and your homework. Confidence intervals for the mean with sigma known. So today you'll learn how to use sample statistics to make an estimate of the population parameter mu, and when the population standard deviation sigma is known. Next time, we will learn how to do it when sigma is unknown. Dun dun dun. All right. So, point estimate. Point estimate. This is a single value estimate for a population parameter. The most unbiased point estimate of the population mean mu is the sample mean x bar. This is the most unbiased point estimate of the population mean. Now, what does it mean to be unbiased? So you might want to take note of this. A statistic is unbiased if it doesn't under or overestimate a parameter. Okay, if it doesn't under or overestimate a parameter. You think about it, okay? So how do we calculate mu? How do we calculate mu? It's the sum of all the data values divided by all of the population. Well, how do we calculate x bar? Okay, x bar is the sum of all the data values in the sample divided by how many are in the sample. Mathematically, these two formulas are the same. Okay, add them up, divide by how many there are. That's the sum. Divided by how many there are, that's the average. Okay. But in theory, they are representing two different things. The first, this is a parameter. And the second, this is a statistic. All right. Now, since mu is equal to mu sub x bar, that implies that x bar is an unbiased estimator of the mean mu. Okay? Now, we talked about a point estimate. A point estimate, okay, a point estimate is a single point trying to predict the probability at a single point. Could be pretty challenging. You think about it, the probability that the actual mean equals some number mu equal to x bar. Well, we talked about it last time when we're looking at the probability of a continuous distribution at a single point. The area under the curve at the single point, the area is equal to 0. So the probability is roughly 0. Yikes. Yikes. So the point estimate, basically what it's saying is if you try to guess exactly what the true average is, you've got no chance, right? almost no chance of guessing exactly what the average is. Okay? So, how do we get around this? How do we get around it? Okay? Interval estimate. Interval estimate. This is how we're going to get around it. Instead of doing a single point like we had here, we're going to do like we did with the continuity correction, and we're going to go out a little bit in each direction, and then we're going to get some area, and that's going to help us. But to do that, it's kind of like doing an interval. It's exactly like doing an interval. Okay, so this is an interval or range of values used to estimate a population parameter. Population parameter. It's a lot better. Okay. I'm going to show you an example why this is better. All right, here's our example. A point estimate of x bar equal to 10. Okay, x bar equal to 10 is the center of the interval. Then we have plus minus margins of error. Margins of error equal to 1.5. That's how far we are off. Okay, we talked about margins of error. Now, let's draw this in a picture. So, okay, yeah. Want to make sure I didn't already have it drawn. So, let's say 8, 9, 10, 11, 12. Okay, so maybe this is my interval. Now, the point estimate is x bar equal to 10. Here's how I want you to think of the point estimate. All right, good old country boy coming out in me. So think of the point estimate kind of like shooting a 22. There's one little round that goes off right where you aim, okay? The bullet, pew, pop, right there in one little spot. That's the point estimate. So the point estimate, x bar equal to 10. Now, the chance of hitting that little target is pretty small. Now, if you're good like me, maybe you nail it on the first try. But, not everybody can shoot as good as the legendary Clark, right? Yeah, y'all know that I'm kind of goofy. Okay, so if you're not quite as good of a shooter, then this is where the interval estimate comes into play. Instead of having a 22, I kind of like to think of this as my shotgun. So my margin of error. I don't really have to aim that well with a shotgun. I just throw it up and shoot. So what does this say? Margin of error 1.5. So that means I'm going to go out 1.5 in this direction. Okay. So that gets me what? 10 plus 1.5 gets me 11.5. So 11.5 here. And then I go 1.5 out in this direction. How do I go left? I do 10 minus 1.5. That gets me 8.5 there. So my margin of error of 1.5 gives me this interval here. Okay, so instead of having a little BB gun or a 22 that shoots just one little old bullet right here, and I'm saying, I bet you bottom dollar that the actual mu is exactly equal to 10. That's my guess, okay? Well, maybe I'm dead on, maybe I'm not. But a better way to be sure you're right is instead of doing exactly equal to 10, you got your shotgun blast that just shoots out all through there. And sure enough, no matter where mu is, whether it's over here, over here, over here, over here, I'm going to hit it no matter where it is as long as it's in this interval. Okay? So which one am I going to be more confident on hitting mu with? Probably the shotgun. So the question becomes, okay, so maybe mu is somewhere between 8.5 and 11.5, right? Maybe. It could, is there a chance that it could not be? Yeah, there's a chance that mu could be way over here. Now, the question becomes, how confident are we that we captured mu? But how confident are we that mu is in this interval? That purple interval that we have there. Okay, that's the question that we are trying to answer. How confident are we? Okay, so this next definition is going to help us. This next definition, level of confidence, C, is the probability that the interval estimate contains the population parameter, assuming that the estimation process is repeated a large number of times. Wah, 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 wah. Okay? So, let me try to draw this up in a picture. Look how beautiful that normal curve is. It's like I've done this 1,000 times. Okay. What's in the middle? What's in the middle? Always z equal to 0 with our standard normal. All right. Now, I want to come up with this level of confidence C. Okay, this level of confidence C. So I'm going to have some cutoff points. I'm going to have some ZC scores. So ZC here and negative ZC on the left. Remember, on the left are negative numbers, on the right are positives. It's symmetric, right? Okay. So let me do, I had a definition. I did it in red up here, so I'll do it in red here. Okay, so everything between the critical values, ZC positive and negative. I'm gonna shade this red. What does this represent? C is the percent of area between critical values. Definition, critical values. What are my critical values? Plus and minus ZC. So plus and minus ZC. The C is your critical values, okay? Separate probable from improbable, okay? So everything outside, let's do this. All right, and blue here, and then blue over here. Look how pretty our picture is. How cool is that? Let's do this for, let's just make up a C, okay? What if we made C equal to 90%? C equal to 90%. If 90% is in the middle, okay, and we know it's symmetric, what does that mean? Well, how much total area do we have under the curve? If we consider all possibilities, there's 100%, right? What do I know about the left side and the right side? When I look at those two tails, what do I know about the area? The area are the same. So all we really got to do is figure out how much area is left. Well, if 90 is used, then that means that there's only 10% left, right? So do I put all 10% over here? No. Do I put it all on the right side? No. What am I going to do? I'm going to evenly divide it. I'm going to put 5% over here, and I'm going to put 5% over there. So you either are going to need to be able to draw the picture and then logically work through it each time to figure out how much area are in the tails. Or you can use this little trick I have where to find the area, all you got to do is do 1 minus the C. Okay, so the C here, 0.90, all right, that's 90%, divided by 2, because I'm cutting it in half. So that's the area and 1 tail. So that's a little trick for you. If you're a formula person, great. Use that formula that I just gave you right here. But if you're like, draw the picture and figure it out, you know there's 90 in the middle, that means there's got to be 5% here and 5% over here. Now, how am I going to figure out what the z-score is here? Well, the table tells me area to the left. So what do I know? Area to the left is 0.0500. Go look it up in the chart. Now, for you that are, bells are ringing, I've already told you to memorize this number. That number is going to be negative 1.645. Boom. All right. If this is negative 1.645, over here on the right side, numbers on the right of 0 are positive. So 1.645, just like that. Okay? So you got your left and your right tail. All right. Hope that makes it a little bit more clear for you. So if there's 90% in the middle, 5% on each tail. Now, what do you think's going on here? Well, going back to this example here, I asked the question, how sure were we that our interval, this purple interval, had mu in it, right? How confident were we? Well, maybe I can say if I have z-scores, 1.645 plus and minus, then I'm 90% sure that my mean falls somewhere between here. Okay, maybe, all right? Now, what do you think would happen if instead of the cutoff points being here, maybe I made them way out here? So now it has some blue area and all the red area. What's going to happen to my level of confidence? The bigger the spread, the wider it is out, the more confident I am. So as the level of confidence, C, increases, the absolute value of the criticals values increase. Okay? All I'm saying is, as my level of confidence gets bigger, 90%, 95%, 99%, the confidence interval gets wider and wider and wider, okay? So it's like, yeah, this 22 might, shoot the target and get it, good. The shotgun probably be better at hitting the target, but if I shoot a bazooka, I think I'm going to be like 99% sure I'm going to blow up the target even if I don't hit right on it. But by golly, if I shoot a nuclear warhead, guess what? I don't even have to aim. Just drop the bomb, right? So the wider your interval, the higher your level of confidence. All right. One definition that might pop up, sampling error. Sampling error. This is just how far away from the mean you are. So it's the difference between the value minus the mean. Remember, the mean is unknown. We don't know what this is. If we knew what it was, we wouldn't need statistics, okay? We're going trying to use data to approximate it. That's why we go out and we gather the sample. but we don't know what it is. So the sampling error is how far off we are. So this calculates the max error based on confidence level. All right, so the margin of error, this is a big deal right here, guys. Make sure you know it. Margin of error. You will be asked to calculate many of these things we've talked about in this little video for your test. So margin of error is the greatest possible distance between the point estimate and the value of the parameter it's estimating, okay? So for a population with mean mu and standard deviation sigma known, okay, standard deviation sigma is known. We know what the standard deviation is. If, here's my Ferrari. Number one, it's a random sample. Number two, n greater than or equal to 30 or population normally distributed. Okay. Then I can use the Ferrari. What's the Ferrari say? E equals ZC, the critical value Z-score, multiplied by the standard deviation of the sample mean, which is equal to ZC sigma over the square root of n. Okay? So this is for a level of confidence C and sample size n. Okay? Now, I can't stress this enough. This is our Ferrari here. So in order to use the Ferrari, we got to have these two things true. Now, spoiler alert. Spoiler. All the problems you're going to work on in this class are going to be random samples. If the sample wasn't done in a random process, then it's junk in, junk out. So with all these textbook cookie cutter problems, you always get a random sample. So really what you need to check is n greater than or equal to 30 or is it normally distributed? If it's both, that's okay, all right? It's okay to have more than one thing, but you need at least one of those two things for sure to be true. So if that's the case, then a C confidence interval for a population mean mu is calculated as follows. Mu is between two values. It's between the point estimate minus the margin of error and the point estimate plus the margin of error. And what is the margin of error? That is ZC sigma over the square root of n and then plus ZC sigma over the square root of n. Okay? This is our formula, right? So what do I say? The probability that the confidence interval, so I'm going to abbreviate confidence interval with CI, okay? That's confidence interval contains mu is equal to C. Remember, C is your confidence level, okay? So that's that probability. All right. So we've got a problem here. We've got a word problem. Random sample. 35 students. Sample mean, X bar equal 25 years from the past studies. It's known that the population standard deviation is sigma equal to 1.8 years, but the population distribution is unknown. AC wants to estimate the mean age of students currently enrolled with a 95% confidence interval for mu. Okay? So I'm going to work this one in another video. Okay, so be looking for a 6.1 video on how to work that problem out. If you get it, great. If you can't get it yourself, watch the video. Okay? So let me do a little bit of teaching between that one and the next problem. So the next video is going to show you how to work this one too. So another 6.1 problems. Okay? All right. So as a little bit more, just writing things out. As the level of confidence increases, the confidence interval widens. Okay? So as the level of confidence increases, the confidence interval widens. All right? The only problem with this is, the precision of the estimate decreases. Why is that an issue? Let's think about this. If I'm trying to predict how old the class is on average, maybe a shot in the dark would be to say a point estimate, maybe X bar equal to 19. Okay, that's just a point estimate. Am I going to be exactly right? I doubt it. Okay, maybe a better guess is, the mean is between 20 and 18. Okay, maybe I'm like 80% sure, my level of confidence is 80% sure that the true average for our class in here is between 18 and 20. Maybe it is, maybe it's not, I don't know. But that's a better guess than just saying, I bet it's 19. All right, I got a better chance. But I can be like 99.9% sure if I said, well, you know what? Maybe the average age is between, I don't know, 5 years old and 70 years old. Yeah, that sounds good. I'm like 99% sure. Well, yeah, my confidence level increased. It went up to 99.9%. But what good does it do me to say that the average is between 5 years old and 70 years old? I could know nothing, and I could know that, right? So the precision, how close I am to the actual true mean, is terrible. All right, between 5 and 70. Golly, I don't even know anything about statistics to make that kind of guess. Okay? So how do we fix this? To fix this problem, we only need to increase the sample size. Okay? Increase the sample size. What do I mean by this? Think about it. The margin of error. How far we are away from the actual mean, potentially. The margin of error is equal to the z-score, the critical value z-score, sigma divided by the square root of n. So if n gets bigger, what's going to happen to my error? The error is going to get smaller, okay? So I need to solve this thing for n. And if you use some algebra, you can solve this for n pretty easily. N is equal to ZC times sigma divided by the error, all squared, okay? That's coming into play because of that square root right there. We just solved for n in that original equation. Now, this is probably going to give you a number that's not a whole number. So if n is not a whole number, what do? Then round up. Round up. Okay? Don't go out and spray the grass with some Roundup, right? Round the number up to the next whole number. Okay, so if I get like an n equal to 14.2, can I go out and ask 14.2 people, do you like ice cream? No, you can't. If you only ask 14, that's not going to be enough. So what do? You go out and you ask 15 people, do you like ice cream? Yes or no? All right? So always round up there. That's what we're doing. All right, so this is used when you're given a C confidence level and E margin of error. So make sure you know this formula. It should be easy give me points for your test. Okay. That's going to be it for this video. Thanks, guys.